Hi, welcome to Intermolecular Forces, Solids and Liquids Part 2. My name is Dr. English. Today we're going to be talking about London Dispersion Forces. Specifically, we're going to look at what are London Dispersion Forces, review of nonpolar molecules, representation of dispersion forces, another representation, and a practice question at the end. So what are London Dispersion Forces? Nonpolar molecules such as helium, diatomic hydrogen, and carbon dioxide are held together as solids and liquids by the intermolecular attraction called London Dispersion Forces. These are the weakest of all the intermolecular attractions, and as a result, nonpolar molecular substances have the lowest normal boiling points of all liquids. In order for London Dispersion Forces to exist, we need conditions of high pressure and low temperatures for such forces to occur. Let's do a little review of nonpolar molecules. Remember, a nonpolar molecule is a molecule that is covalently bonded with symmetrical distribution of charge. So let's look at diatomic oxygen. If I draw oxygen, there's oxygen right there, and I know that oxygen has 6 valence electrons. So 1, 2, 3, 4, 5, 6. And here's another oxygen over here. There we go. 1, 2, 3, 4, 5, 6. I can connect these two oxygen atoms together by drawing bonds like here and here. At this point, these two oxygens are sharing these 4 valence electrons. So if I were to redraw this, I can say that oxygen has a double bond between its two atoms, and also including, of course, our 2 lone pairs on this oxygen and our 2 lone pairs on this oxygen. There is equal pull by each oxygen atom in both directions, and because each atom is pulling equally on these shared electrons, the molecule overall is nonpolar. Let's look at another example. Let's look at methane. Methane is a carbon in the center, hydrogen, 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 and hydrogen. I can use electronegativity values and assign them to all the elements that make up methane. I know that each hydrogen has an electronegativity value of 2.2, 2.2, and 2.2. The carbon has an electronegativity value of 2.6. So if I had to draw polarity arrows from my more electronegative to my less electronegative, I would have my arrows pointing inwards towards the carbon. And when I look at these arrows, I can see that these 2 arrows cancel each other out and these 2 arrows cancel each other out, because if they're pointing in or away from each other, that's basically telling me that there's an equal distribution of electrons all towards the carbon. Because of this symmetrical distribution of electrons, methane is a nonpolar molecule. Let's look at a representation of dispersion forces. Here we have diatomic nitrogen. Now remember, no compound is actually static. The electrons are always moving. So at any one point in time, these shared electrons in the center might be more towards this nitrogen or pulsating back over towards this nitrogen. So the electrons are always moving from one end of nitrogen to the other. We can represent this movement of electrons as one nitrogen being slightly positive and the other nitrogen being slightly negative, as the electrons move in a dynamic fashion. If you have this occurring and you move these nonpolar molecules close to another molecule, we do something known as an induced dipole. We know that diatomic nitrogen is a nonpolar molecule, but as soon as we get them close to other molecules, we induce a dipole, and we have one end that's slightly positive, one end that's slightly negative. As a result, if there's enough pressure and cool enough temperatures, we can have dispersion forces existing. So the 3 blue dots between each one of these molecules shows this very weak force of attraction between the molecules that could make liquid nitrogen. Let's look at another representation. Carbon dioxide. Carbon dioxide is represented as a carbon in the center, an oxygen on each side, connected by 2 double bonds. Again, the electrons that are shared between the oxygen and the carbon are not static. They're dynamic. So at any one point in time, all of these electrons might be pushed closer to this oxygen and then pulsate back to this oxygen. So it's a dynamic process. As a result, if you get a whole bunch of carbon dioxide molecules next to each other, at any one point in time, one end might be slightly positive and the other one might be slightly negative. If we throw in our dots, again, we can see these really weak forces of attraction between one end of a molecule of carbon dioxide and one end of another molecule of carbon dioxide. This representation might represent liquid carbon dioxide. We don't have a very ordered pattern here. They're not very close together, but we can see some really weak forces of attraction. If we increased our pressure and lowered our temperature more, maybe we could make dry ice, where the carbon dioxide, in a very perfect world, all line up next to each other, get pushed together, and we can again see these weak forces of attraction between slightly positive oxygens, because all the electrons have gathered over here, and slightly negative oxygens, because the electrons have pulsed over to this side. So in each of these cases, where maybe this one is representing a liquid and maybe this one is representing a solid, we can see dispersion forces happening in this particular compound. Let's look at a practice question. Hydrogen can exist as a liquid only at very low temperatures. This is primarily because the attractive forces between the molecules are hydrogen bonds, ionic bonds, covalent bonds, and dispersion forces. So take a moment, think about the question, choose your answer, and we'll come back and see if you're right. Welcome back. Which one did you choose? If you chose dispersion forces, because that happens to be the topic today, you're right. Hydrogen is represented as a diatomic, H2. And if we were to draw this out symbolically, we'd say H-H. Because this is a nonpolar molecule, the only type of force of attraction that could work here are dispersion forces. So what did you learn in this tutorial? We talked about London Dispersion Forces. We did a little review of nonpolar molecules. We looked at some representation of dispersion forces. We looked at another representation of dispersion forces. And finally, we did some practice questions at the end. Need more help? Feel free to contact me. Have a great day.